Hi everyone. So today we will be learning Kruskal algorithm. It is an algorithm which is used to find minimum spanning tree. So let's see what we will do in this video. So after watching this video, you will get to know what is a minimum spanning tree, what is the Kruskal algorithm, its pseudocode, running time, and why is it correct. So let's straight jump into what is a spanning tree. So a spanning tree is a subgraph of the given graph which have v vertices and e edges which have the following property that all the vertices should be included in that graph and it should be acyclic. So from this we can conclude that the total number of edges which will be included in the graph is v minus 1, as we want all the vertices should be included and it should be acyclic. It is only possible in the case when there is v vertices and the number of edges are v minus 1. So you must be wondering that what is a minimum spanning tree? It is the cost which makes it a minimum spanning tree. A cost is the sum of weights of the edge which are included in the tree. Therefore, a minimum spanning tree should have minimum cost among all the spanning trees. So let us see the example of spanning tree and minimum spanning tree using this graph. So if I include the edge with weight 4, 5 and 2, both of the properties of spanning tree which is acyclic and that all the vertices should be included are satisfied. As we can see, all the vertices are included and it does not form any cycle. And the conclusion that we made that the number of edges should be v minus 1 have also been considered, as we can see that the number of edges are v minus 1. So the cost of this graph will be 4 plus 5 plus 2, which is 11, which is also displayed using this figure. But we can see that this is not the minimum spanning tree because there also exists a graph which have a less cost than this spanning tree, which is this one. As if I include the edge 1, 2 and 4, again the property of the spanning tree will be satisfied, which is all the vertices should be included and it is acyclic, and its cost will be 4 plus 1 plus 2, which is 7, and it is minimum among all the spanning trees. So let's move on to steps required to perform the Kruskal algorithm. First of all, we have to sort the edges in the increasing order of the weight. We have to pick the smallest edge and add the edge to the tree only if it doesn't form a cycle. So we have to repeat these steps for v minus 1 times. So before starting, let us see what is needed to start the algorithm. First of all, we will need an array list which will store the vertices which have been included in the MST, a label array which will store the label of the vertex. So let us see the functions which will help us finding the cycle in the Kruskal algorithm. Mainly there are two functions, which is a find function. It takes an argument u, which is the vertex, and returns the label associated with that vertex. The union will take L2 and L1. These are the labels. The label will have the list of vertices which have a label L1, and L2 will have the list of vertices which have label L2. So if the number of vertices with label L1 is more than that of L2, we will add the vertices with label L2 to the list of L1. Now the L1 will have the vertices of L2 plus the vertices which were already included in the L1, and we will now have 0 vertices to the label L2, or we can also delete the label L2, and we will do the vice versa if label 2 will have more number of vertices than that of L1. So now let us see the pseudocode of it. First we have to sort the edges in increasing order of their weight, and we have to obtain an array. We have to run a for loop to iterate through that array. Let the edge ei be the edge we have got from the array and which have two endpoints ui and vi. First we have to see if the label is same or not. If it is not same, we have to add ei to the array list which stores the edges in mst, and then perform the union function on the label of UI and VI and do the necessary as told in the previous slides. So now that you have understood the pseudocode, let us see it's working using this graph. So I have sorted the edge by increasing order of their weight. So after sorting, I will obtain this array which is 1, 2, 3, 4 and 5. Now I'm labeling each of the vertex as A, B, C and D. So starting from the first edge, which is 1, and as find of A is A, find of B is B. It does not form any cycle. I will add the edge 1 to the MST. So this edge will be included in the MST. I will change the label of B to A. You can also change the label of A to B, as both of them have the same number of vertices. So moving on, we have 2. So label of this vertex is A and this vertex is C. So it also does not form any cycle, and we will include this edge 2 in the MST and change the label of C to A, as there were less number of vertices with label C than A. Now we have 3 for the edge 3. Both of them have the same label, so we will we will not do anything. Moving on to 4, label of D is D, label of A is A. Both of them has different labels, so we will change the label of D as A and include the edge 4 to the MST. Now the resultant MST will have the weight 1 plus 2 plus 4, which is equal to 7. So we can see that it is the MST, and hence the Kruskal algorithm will give us the minimum spanning tree. So now let us see its running time. The sorting of the edges will take E log E times, and the union will take log V times. Why? Because if I take L1 have number of vertices as V1 and L2 has number of vertices as V2, and if V2 is greater than V1, I will I will add the list of vertices to label V2. Now L2 will have number of vertices as V2 plus V1, which will be greater than double of L1. So now as we have number of vertices as V, it will run for at most log of V times of base 2. So the total time for the for loop is E into log V, as the for loop is running for at most V minus 1 times, which is E. So overall time for the algorithm is E log E, the time for sorting, and E log V, the time for the for loop. And we know that E is less than equal to V square. So by replacing E as V square, we will get 2E log V plus O E log V, which is approximately equal to E log V. Moving on, let us see why Kruskal algorithm is optimal for the minimum spanning tree. So let us assume that there exists a optimal solution O dash which have the following edges included in its MST, which is O1, O2, O3, O4 and many more. And in the case of Kruskal algorithm, which have the following edges G1, G2, G3 and G4. And note that both of them are in increasing order of their weight. Now if I add G1 to the list of edges obtained from the optimal solution O dash will form a cycle. Now if I remove an edge which have the highest weight in the cycle, let's say it is O2, now the optimal solution will be O dash union G1 minus O2. Now this optimal solution will be spanning and the cost of this solution will not increase. Why? Because G1 was the least or the cheapest edge in the graph. So it is not possible that it will increase the cost, which is the sum of all edges. So now we can add G2 and remove some edge from O dash, and then again repeat this process and convert the optimal solution into optimal solution having the edges G1, G2, G3, etc. So now we can therefore conclude that greedy is the optimal solution. So let us go through some claims for the correctness of the Kruskal algorithm. The first claim says that if all the weight of the edges are distinct, then the cheapest edge will always be included in the optimal solution set of edges. Now let us prove this by contradiction. If I assume there exists a solution which do not have the cheapest edge, which is E1, and we know that MST will have V minus 1 edges and V vertices. So by adding E1 to the list of optimal solution of edges, we will have V vertices and V edges. Therefore, it will form a cycle. So by removing the highest weight of edge in the cycle, the cost of the tree will decrease as E1 was the cheapest edge in the graph. Therefore, it is the contradiction that the solution does not have the cheapest edge. Now let us see another claim, which is at the end of the Kruskal algorithm, the MST obtained will be connected. So if I assume there are two sets, let set A be the vertices which are included in the MST, and set V minus A, which are the vertices which have not been included in the MST. So we know that the graph is connected. So there must be an edge between the set A and set B, which was V minus A. So it is not possible that our algorithm would have not picked that edge, as if we included that edge, all the properties will be satisfied, that all the vertices will be included, and it will be acyclic. So let's see what we have got for you in the next video. It is another MST algorithm, which is Prim's algorithm. That's it for today's video. Thank you.